Hello, everybody. Welcome back to the Brain Stream. I'm here with Harrison. Harrison, do you want to say hi?
Hello, everyone.
Today, we are speaking with Garret Flynn and Josh Brewster. Garret is a graduating master's in media arts, games, and health at the University of Southern California, with a background in computational neuroscience. Josh has been building open source sensing hardware and software with emphasis on creating low-cost neurofeedback tools and using the latest design resources to make these tools more accessible. Brains at Play, which is their company, is developing an open source brain and medical sensing tool with modern web technologies and low-cost IoT hardware. They're helping pave the way for a future of community-led health technologies. Garret and Josh have also worked on MyAlice, an overdose detection tool, which is currently in development. Thank you guys so much for joining us.
Yeah, welcome.
Thanks for
Glad
having
to
us.
have you.
Thanks.
So let's get started with your guys' personal background. So, I know we mentioned your majors here in the introduction.
So the beginning of my story is really that I read Neuromancer, a book by William Gibson that described full body virtual reality access with the brain implant sometime around early high school. And that got me really excited about the brain and the possibilities of augmenting largely sensory experiences, but also things like providing motor feedback for really enhancement applications. It was largely aspirational, very idealistic, but it got me excited. And so after that, I studied neuroscience sort of at home. I knew that's what I wanted to study in undergrad, and that kind of led me to pursue my own path in high school. I didn't quite drop out, but I didn't participate fully. I was largely just sitting in class and reading and otherwise thinking through a lot about my future. So I ended up graduating early by applying to the University of Southern California's resident honors program. So that allowed me to apply as a junior and just go straight into freshman year of college. So for me, the choice to go to USC was more practical. I didn't want to stay for senior year. I didn't know that there were other programs like this in the US. So this seemed to be like a golden ticket to get out of there and start pursuing what I really loved. And then going forward into now this master's program, I engaged with a lot of people in the neuroscience community here, particularly the Center for Neural Engineering. So they built a hippocampal prosthesis. So it targets the memory center of the brain and basically stimulates to restore memory function in cases of Alzheimer's and dementia. It's tested in patients with intracortical electrodes that are being monitored for epilepsy. And they have substantial memory improvements in those cases. So that was some really exciting work that I dug into early in my time at USC. With that same faculty member, I ended up pushing into work around ethics and public engagement. I worked with commercial neurotechnologies like the Open BCI and the Muse, and then realized all of the immense problems with actually programming software for these technologies, and just a lot of the common challenges that developers face. And that led me to pursue different directions in development. I engaged with the arts and sciences communities on campus. And ultimately, sort of that led me to the work that's currently happening with Brains at Play.
That's great. It's good to hear that the resources were there and available for you, because like it's been really interesting seeing the neural engineering programs pop up around the country and around the world, because even like when I was looking at college like 5-6 years ago, it was just that really wasn't a thing that was out there. So I mean, somewhat on like the master's and graduate side, but it's really interesting just to hear that those opportunities were there. And that's very cool.
And I'll be honest, the most helpful resource in this case was actually Makerspace on campus. It's affiliated with what's called the Polymathic Academy. And they provide access to more expensive hardware. So that includes VR headsets, that includes high performance computers, things like that. They funded me to get an Open BCI headset. So we purchased the $1,600 Daisy Cyton with an Ultra Cortex. And that is really what kickstarted my developments in this space. I could not have done it without them. And despite learning a lot in the computational neuroscience curriculum, it really was not applied at the undergraduate level. The closest I got to actually working with brain data, or at least something similar to brain data, was programming like a cell model in Excel. So programming like a neuronal simulation in Excel, doing a little bit of simulations of receptive fields in MATLAB. But beyond that, it was all like totally not aligned with actual neuroscience data. It was just simulations for biomedical engineering and the like. So it left me wanting a lot of things. And I think there's a lot of improvements that can be done within that sort of educational realm. But it was a lot of fun. And I learned a lot. It gave me a very good jumping off point. But largely that educational track is still oriented around going into a PhD or further studies.
Interesting. Very cool. Josh, I'd love to hear your background building off of that, and then love to know how you guys met, and then where the ideas for Brains at Play and your various other projects came from.
Sure. Well, it's kind of hard to say exactly how I ended up here, but let's see what. So I started. I'm from Alaska. I was born there. I mean, I lived in Vermont a while too, but mainly I grew up in Alaska. I was there for middle school through high school as well. Then I started studying. I was always interested in like whatever, philosophy and like literary stuff, and then later got more into psych. And I always loved computers. But then I decided once I graduated high school that I was really hell bent on working for NASA. So I started studying aerospace engineering. I got to go intern down in California at NASA Edwards after my freshman year. And then when I started going to Cal Poly for like a serious aerospace, it was so funny. Like I knew nothing. So I pretty much just walked around and got to know people. But I did get to work in the Dream Chaser lab. So I got to do some debugging for a flight simulator for like a space shuttle. And,
That's awesome.
And I got to teach Lee Archambault how to fly his own spaceship. So I felt pretty cool. I knew nothing else, but whatever. And then, so then I started going to Cal Poly, decided for one, the pace there was not for me. And then aerospace engineering in general was like, okay, I get to work on like some of the coolest stuff in the world, but I have to basically sell my soul to the military industrial complex and the things I want to work on. Just like everyone else at NASA, I would have to be at the whims of like congressional funding and who's in power essentially. And it kind of all just rubbed me the wrong way, especially being at Cal Poly, which is a very like corporate sort of oriented, like your finals in an engineering program there is to do like a job interview essentially where you build something for some private company and then they hire you or, they connect you to whoever. It's a sweet deal, but like for me, like my character, it just wasn't for me. So I go back up to Alaska. I went to start studying computer science up at UAF, and then that was cool. I learned how to do C and Python, and my engineering teacher in Juneau, she taught me how to do MATLAB. So I got exposed to coding, but I wasn't feeling like it was like, I'm learning all this really hardcore math and stuff, but somehow it didn't feel serious enough for me. So then I switched into psych because I was like, okay, well, I'm good with people. So maybe I could be like a social worker or something. And then I'll just do the tech computer stuff as like a hobby. And then that was just like a disaster. Well, the school was having budget issues. The professors were all really stressed out. And then I don't know. And then I was basically on the tail end of them completely stripping out the liberal arts program. So it was not serious at all. And I was just like, I literally stopped doing like my classwork and shit because I just couldn't even, I was just like, this sucks. This is pointless. This is a waste of my time. And I spent all that time instead just reading like papers and books and, teaching myself the things that I wanted to be learning, which was more like high level, like cognitive behavioral science and learning neuroscience and all these things that I could, if I asked my professors any of these questions, they didn't know like a thing about like it. And what I found this really great book called, I can't tell the story on this podcast about how I found that book, but it's called Brain Computation as Hierarchical Abstraction. And by Dana Ballard, who's like a UT Austin
rolls off the
professor.
tongue.
Yeah, yeah. And it really is.
Nice.
And I was reading like neurolinguistics lectures. Yeah, I know I've had some practice saying that title. But that was finally like some serious exposure to like computational neuroscience and like machine learning. And I had a really good friend growing up who was into a lot of this stuff. And so he had sort of gotten me turned on. And then he dropped out. He's like, I'm not going to do it anymore. So I was like, I'm going to carry the torch. I'm going to learn this stuff. And from there, I don't know. I was having a lot of like personal issues as well. So I ended up being like, well, I feel like I'm wasting my time in college anyway, and I don't really have the patience anymore to deal with this. So I dropped out. I started working with my friend who's a ham radio guy in his garage. So he taught me how to build electronics, and he's cool. Yeah, I got to learn a lot of the basics of like analog engineering, and he showed me how to design high frequency antennas. So some cool stuff. And then he helped me build HEG. This was like 3 or 4 years ago now. He helped me build the HEG, and it's a FNIRS, so function near infrared spectroscopy. It's just one sensor and a couple LEDs, and then you can get brain oxygenation, like relative readings. And at the same time, I started learning a lot of I had approached psych from more of like I had a literary education, so I understood sort of where psychoanalysis and like neuroscience, like where that nuance is between, when to use both, and so I started really getting into like, okay, understanding brain structures and like computation and all this cool engineering stuff, but also at the same time, how does this turn into like our psych? And then how do you then turn that into better tools to actually help people with psych? And so that's when I started getting exposed to like EEG and neurofeedback, and my favorite's HEG, just not just because I'm trying to sell them, but I mean, legitimately. And the story around the HEG was really endearing to me too. The guy whose patent, well, there's a couple guys, but the patent that I used to base my design off of, which it like when expired that year, I started playing with this stuff. And then the guys who started it, one was like he was like a veteran who he was protesting the war, so he got discharged. And then his partner, the Herschel Toomey, was a scientist who he built some of the original like EMG equipment, and he's a doctor of science, and he had dozens of patents on different electronics hardware. And he got into I got to read his journals. He got into biofeedback by first he was studying like incontinence and other things, like after people have strokes or whatever happens, and then they get older. So then he was looking at like muscle signals to help basically people retrain these things. And then it's cool because you can see that's where he starts to be like, oh, well, what about brain signals? Like, is there some sort of similar relationship there where we can actually train like cognitive and emotional reactions in a similar way as we can retrain our muscles? And so sure enough, he finds that. And then he got into FNIRS because he realized the main thing he cared about training with EEG feedback showed up, which is just attention for him, showed up as it shows up more clearly as a rise in metabolic activity wherever you're measuring that. And then that's really easy to measure with FNIRS, that's what you're measuring. It's the red and infrared light.
That makes sense.
You get reflected back. It's your hemoglobin. It's also some of that infrared is some of just the raw metabolic activation going on in there. So you get information about both things. And then now I'm learning how to design tomography and all this stuff. I'm working with Garret on. So this is the other part of the story of like, okay, why am I doing this now? I realized there was a huge gap. Like for one, this device was like $1,000 still when I was working. Well, several $1,000s. It's still not much better. Device, right? Yeah, the HEG.
Yeah. Real quick, I just want to quickly interject. HEG is hemoencephalography. And do you want to explain quickly like what the goal of using an HEG is in general?
Yeah. So, I mean, it's relatively simple. Like the real goal is you're trying to learn breathing exercises and you're trying to learn better self-regulation. Because what happens is when you get stressed out, it actually impacts blood flow in your brain in a big way. And if you have less like resilience, basically to stress, one of the bigger things you can measure is actually a drop in, like, especially frontal, they call it hypofrontality. So a drop in frontal blood oxygen content. And then that correlates to essentially a loss of consciousness. And then this actually correlates to certain symptoms of like PTSD or ADHD or people who get overwhelmed, like if they have autism or something. And so there's these certain things that show up in anybody who has issues coping with stress. And so you can actually train this. And the way we learn how to do this is we just learn to breathe, and we learn to have some sort of self-regulation, mostly unconsciously, whatever our parents or friends or whoever can teach us. But then this is more directly like, we can actually also measure some of this, and then we can directly mediate that with like breathing exercises where you're trying to essentially maximize blood oxygenation in your brain, in your cortex. And then that should correlate with, more conscious functioning, especially better frontal, executive functions. And this really does seem to be the case. So really it's like an assistive breathing technology. But then it has some psychotherapeutic application as well. Cause you can start to like, this can help you normalize your physiology because you get a measurement that helps you understand if you're doing like, if the breathing exercises are helping you oxygenate more. And then once you start to normalize that, you can start to explore more of like your psychological world, and you get a baseline from there to work on. So that helps people a lot. This is where a lot of therapy even is you're just like working through stuff while you're also trying to keep people sort of at a strong baseline, so that they can learn to cope with these things better, be more resilient. So the idea is you take that and try to build a tool for that, automate it.
That's interesting. So is this so it's kind of like a neurofeedback device, but you have a higher level of specificity or more information that you can get out of that because you're able to look at the blood oxygen level, and that gives you more in terms of stress.
So if you do tomography, you can actually learn more than you can with EEG, in my opinion. It's even better in combination because then you get electrical signals and you get so what's better with the FNIRS compared to EEG is with EEG, unless you can do implants, right, you're measuring scalp activity. And so there's obviously a lot of noise. There's a lot of stuff that just does not correlate at all to anything that's going on inside there. And then you need a really high density of sensors to get meaningful information, like truly meaningful information. I mean, you can do like control things and other stuff, but you can't really learn much about the actual, like the mind. Now, with FNIRS, you're actually getting an image that's from the depth that you're measuring. And then if you take, like my headset's just one sensor, but if you take a whole array of these sensors, what you can do is you can, you take the coordinates of your sensors and then you build a tomography image of the readings you're getting back, and you use estimations of the light paths that we know are being created by that reflection pattern. And so you can actually build a 3D image, and it has parity to fMRI. What's special about it is you can start to do this in real time though, which I don't think you can do with fMRI. So what you end up with if you do a proper FNIRS tomography image is a 3D map of like cortical activation, and you can sort of see depth of where those activations are. And it's highly reproducible as well. So you get very
so the goal is to sort of do like a live data reading with this, but like an FNIRS that has higher temporal resolution, pretty much, right?
Yeah, well, I mean, what I want to get into imaging because I mean the biofeedback's cool. Like it's obviously a pretty powerful proposition, and then but beyond that, like I want to validate that. So it's cool because I can take the same tools and I can start to do imaging, and then my long term goal, like with this FNIRS biofeedback, is to show that you definitively are having like better perfusion or whatever, better activation if you're going through like high stress, like through a training process, because that would show like. I don't know. You can kind of think of there's all kinds of therapeutic things we could start to validate. If that's
no, definitely. So that makes a lot of sense. And that's a really cool kind of trajectory that you've gone on to come into neurotech. And then, you've been working on that for a while. And I like kind of something that I hear in both of your stories is that like Garret, you were you had more of a formal background, sure, in neuroscience, but you still ended up, most of your learning about neurotechnology was self-taught. You were able to be funded and get access to this device, but now you have to kind of, go to the internet or to mentors or, whatever route you went to try to learn how to do this. And it sounds like both of you have kind of gone that route where it's just the interest has driven you to learn about this. And from what I understand about what you guys were talking about, brains at play, like it seems like there's part of that mentality that's sort of driven the underlying concepts of that. So I'd love, if you could both speak to how you met, where that idea came from, and kind of what the objectives are and like the mission underlying brains at play.
Yeah, I can tackle the first portion of it at least. So at least from my perspective, I was working on a public engagement event called Livewire, where we were going to have people go to the USC library and wear open BCI headsets. It was going to be a speculative future. It was set in like 2045. And it was essentially a giant matchmaking service like Tinder, LinkedIn, whatever, where, we would cycle people through, about 6 people wearing open BCI headsets. The synchrony of their brains would be calculated, and then you'd spit out who they were most similar to. Of course, at the same time, raising a lot of ethical considerations around, how is this data used? Is all of the code open? What are all of the concerns that people might have? And of course, sourcing those at the same time. So keeping an eye on what people actually experience and see if there's anything new that pops up. I got $20,000 worth of funding to do that, and then COVID hit. So that meant no library. That meant lots of restrictions. And the worst part was we didn't know how long it would take until things would reopen. So I spent probably a good 6 months trying to develop an idea around this, being like, oh, well, in the fall, everything will open up again. It's going to be fine in a year, right? No. So that didn't happen. And I, at least somewhat quickly, pivoted to, well, if I can't record the synchrony of people's brains in a physical setting, what if I can record their activity at home and then compare them at the same time? So that naturally led me to web technologies, the first prototype I built. And another thing to add is that this was also for an undergraduate thesis in media arts. So I had a minor in media arts, and that sort of led me to a lot of this artistic and public engagement considerations. So the first prototype was using BrainFlow to get OpenBCI data into Python and stream that over WebSockets to a browser, and generally enable that sort of distribution. So you could actually forward it to other people connected to the same web page. I also used Muse.js and got that integrated. So that uses Bluetooth to interface with the Muse device directly from the browser, requiring no additional software dependencies. And at that time, I had no idea what Bluetooth or Web Serial were. But I was really excited about what I was building. I integrated, again, this sort of whole multiplayer system on the browser using BCI data. And I presented that to Neurotech SF. So that's one of the Neurotech X arms in San Francisco. And Josh was at one of those meetings. So really what ended up happening is I was like, hey, I have this, BCI system that forwards people's brain data over the internet. And it's, using web technologies to create this like a weird multiplayer, multi-user system. And Josh followed up with, hey, I built a web interface for my HEG. And so he was using Web Serial and Web Bluetooth to interface that device directly with the browser. I was like, oh my God, like I didn't know that existed. Let's try to do something. We left it off for about 3 months. I was preparing for that event still. I didn't know JavaScript very well, but I was still learning it at the time and developing best practices. And at some point, we just locked down into about a 6-month development grind.
I hit you up and I was just like, hey, let's do this now. And then, well, it started as like, okay, let's work on like, because I was working on the free EG32. I mean, we're perpetually working on 3, but trying to build an interface for that. I built a cool, so it lets me, I can stream the free EEG. So I can stream 32 channels of EEG into the browser, and then I can send it to a worker, which can then run whatever it does, just fast Fourier transforms on the GPU from the worker. So then it's like offloaded from the render thread. It's very fast. I can run hundreds of FFTs per 10 milliseconds or whatever. It's really cool, and this is just using some fragment shaders, but it's done through the browser context, like native browser code, no Python, nothing. And I was like, oh my God, it took me like 3 months or 6 months to get that working, just like being from like theory to like, okay, how do I program an FFT and how do I do a GPU kernel? How do I do a web worker? What the hell is it? And also, how do I process the 32 channels of data like fast enough so that I don't crash the damn browser? So I had to learn all that, but it took like 4 to 6 months. And then I got a working prototype. And then a few months later, Garret and I were like, okay, let's actually build a platform for browser, like EEG, FNIRS, whatever. And then it's been dawning on us. I mean, it was dawning on us then. It's still dawning on us more and more of like, oh my God, web technology is like, it's like the real deal now, where you can actually get, you do high performance computing plus all the user interface, plus all the networking, and it's all in, one giant set of languages. And plus you can do whatever interoperability you want, blah, blah, blah. So, we're at this point where it's like, we need to implement this now if we're going to do like proper scaling tech. Plus it's cheap. I mean, I got here because I was like, I'm going to work with $10 equipment and I'm going to be one guy programming a whole interface and a microcontroller like system. So like it was natural for me to end up on web, but then now it's like, oh, plus this tickles all my like inner computer science fancies of like high performance computing, plus, high distributable, like, it's highly distributable, blah, blah, blah. All these things that in the development world are a complete nightmare. And then in terms of best practices, I don't think anyone's really developed them, like we all kind of know things about, like how to, use memory and all this stuff. But then putting all of that together into one functional system, it's a ton of work. And web removes probably 95% of that. But now it's like also performant. So now we're just trying to build a general thing. Yeah.
Much to the chagrin of a lot of software engineers, the future is in JavaScript. For
I keep
software.
saying that, and I was like convinced C++ was it, because it's like, wow, you can do anything in C++, except like, now you have to type systems and you have to do function overloads, and nothing's like as easy to do when you really want to scale it. And now this is where it's at. And so okay, and then the other side of this is we're like AGPL, and we're pretty much religiously AGPL, and that's because we have this notion that, okay, this is going to be real medical infrastructure that's going to be serving people, not just like cute neurofeedback devices and products, but like legitimately it's networking and information technology and it's really powerful and it saves us a ton of time. So like hospital systems, whatever, we're working on a rehab networking project. All these things, we can essentially build them all from the same subset of, or superset of whatever word you want to use, of tools. And then a lot of that underlying infrastructure, like WebSockets or a lot of the UI elements. I mean, like Google's pulled this off in a lot of ways, right? Where they have a very generic set of tools, but it works in a billion cases. Like we're thinking about like, okay, solving that problem, but specifically in a high performance, like, sensor to front end like thing, but making that all open source. So it's like, okay, we have the best solution, but it's also like free and open source. So anybody can learn this stuff too. And, it's not going to be locked up somewhere, because I think in a longer term sense, like that's really important. I mean, reducing the cost of healthcare because the technology is overpriced or takes too much time and money to develop it.
Right. And that's a good segue, I think, into, what's the main problem that you guys are really trying to solve with Brains at Play?
Probably that, like,
yeah, that's what I figured.
I would say that's the big one, and then in the short term, it's like, okay, we're trying to just build like some apps and some stuff that, it motivates us to build these libraries correctly and then to sort out that whole modular infrastructure thing. And then, but that generalizes into whatever use cases. So I don't know, we might be working with a lab here in a month on like doing a version of Brains at Play, like as an educational software, but still building on the open source.
Yeah, I would say, sort of one way to augment that proposition as well is that what we're trying to do is make high performance computing on real-time data streams in the browser feasible and easy. So that's, evidenced by Josh's earlier.
It's feasible. It's just, we got to make it easy now and make it a set of one-liners that don't crush you into one mode of thinking, Yeah.
And so that involves a lot of different threads, essentially. So we have to make it easy to get data into the browser. We have to make it easy to offload data into threads, off to servers, easy to configure applications, and then, easy to make applications, at least in the early phases of brains at play as well, was to make them easily controllable through whatever inputs you have available. So, if you can't move your arms, how do you actually do this? You could use eye tracking, you can use a BCI, you can use a bunch of other alternative communication devices. But how do we make applications on the browser something that anybody can use? Setting up pipelines to, again, make this something that's easy to configure, or even brain dead to just put into an application or, a Chrome extension, plop into a web page, and there you go, it works.
So really laying the framework and the groundwork for this, this processing of large amounts of data and being able to use it in real time all through a web framework. That's sort of the goal with this.
Yep.
And then doing so in a way that is sort of virally open. That's the whole AGPL side of things. So, if you contribute to our applications, we want people to contribute. And one of the promises we make is if you contribute, everything that you do is maintained as this sort of open standard for the community.
And AGPL, for those who aren't as familiar, is an open source software license. Go ahead, Harrison.
Yeah, so I'm curious with all of that. I definitely see the tremendous benefits of making this open source and putting it online. I mean, the collaborative elements, you can access it wherever, you can send it and work more easily with healthcare providers. That all makes sense. But I think one red flag that might come to mind is, how is the data being stored? How are you ensuring that is being safely controlled for, especially when you have this open to a community where people are developing different applications? So it's less of a problem right now, but especially when that data gets more and more sensitive as technology gets better, how do you account for issues like that, potential vulnerabilities?
It's all local. All our libraries are built for client side stuff. And then there's different networking tools. If you want to do end-to-end encryption or blah, blah, blah. And a lot of this stuff is canned. We haven't gotten that far to implementing that. So when you're gathering all that EEG data, it's not going to some server that we have. It's just stored in your cache. there's a permanent caching system in browsers. And you can store arbitrary amounts of data. It's also optimized so you can pan across giant data sets. And so that's just all stored in your own computer. That's secure. And then, we're messing with Google Drive integration, right? So then it goes to your own Google account. In terms of doing larger scale databases, plus it's easier. It's cheaper too. Oh my God. Clouds are so freaking overpriced. No, but in terms of doing then translate that into now say we have a whole population, we want to gather data from them securely and anonymize that, blah, blah, blah. For one, there's a lot of existing tools for doing that. Two, we're going to make sure that works, but we're just not quite there yet.
Yeah, one of the beauties of actually approaching all of this from the perspective of open source as well is, your vulnerabilities are out in the open. That's a problem. But a benefit of it is that all your vulnerabilities are solved in a way that is open, right? And so that you can sort of generalize to any system that's created with this infrastructure. So that's sort of the goal, is once we get to the point of promising, this is all going to be put on a server, we want to know how you can get around this. We want to know how we can make this better. And at the end of the day, then that means that anybody using this infrastructure will benefit from those contributions. I do also want to mention that one thing that we're exploring as well is on the side of data management. Outside of databases, we're also looking at different ways to store the data. So what we've really previously done is just stored them as JSON strings, right? That's what we do in IndexedDB, Josh, or is it CSVs?
CSVs.
Okay, well, we're storing them in a format
CSV, and then it turns into a binary. If you want to know.
Yeah. But essentially, that's something that's very easy to use. You can pull it into Excel or Google Sheets and then do some analysis on it.
The unfortunate industry standard.
Yeah, but it's not necessarily built for brain technologies. And one thing that we want to do is integrate data standards. So there's emerging standards like BIDS, so that's brain imaging data standard, or brain imaging data structure, and neurodata without borders, which are both emerging standards for handling neurophysiology data. One of them is, probably going to win. Maybe there's going to be multiple standards for multiple different things. But suffice it to say that what we would prefer to do, or at least what I would prefer to do, is to stream data from the browser directly into one of these formats, or allow for easy translation from, say, the CSVs that we previously had into one of these data standards, and then be able to, create interoperable tools that allow for you to analyze these post hoc, potentially even using some of the infrastructure that's being developed by research labs. One of them is the Dandy archive. It's a distributed archive for the NIH Brain Initiative, just pushing all of that data there, with appropriate permissions from the user. It's another way to ensure that we create more openness. So that would, for instance, be like an open data archive.
Cool. Well, hey, we're going to get a little bit more into, the plan for releasing this platform and all that stuff. But I just quickly want to ask, how specifically can listeners who are interested in supporting Brains at Play or open source software in general, what do you think the best way that they could support you guys or any other open source project?
Well, we need to start promoting our open collective page. No, otherwise, open source is like, it's a problem right now where you have a lot of people developing a lot of stuff for free and they don't get compensated for it. But also, like, we don't necessarily have, there's no like system in place to like publicly fund a lot of this stuff. So I feel like there's like some policy changes we need, or at least like universities need to get really serious about this stuff. And I think it's starting to happen. And then beyond that, I don't know, there's plenty of ways that like every open source like group that's serious has ways to fund them, or they
donations.
Like, we're going to come up with
sort
products
of thing,
too,
intellectually contributing to the projects, maybe.
Yeah, hire us if you have something that's not going to steal too much of our time, or just make it open source, and then we can do whatever.
One thing that I've gotten a lot better with as well is when I start a project, try to find some precedent, because you don't need to build everything from scratch. And if there's something that is similar to what you're doing, particularly if it's from a well-supported organization, then what would be preferable is contributing to that project rather than trying to spin up your own, handle all the marketing, the maintenance, et cetera, right? And another angle for us is that what we want to do is be very community oriented in addition to being open source. So, some open source projects are giant monoliths and you contribute with, GitHub issues and you submit your changes. And what we want to do is actually be like deeply engaged with our users.
Yeah, but, I'd like to echo that sentiment of, especially in a field as complex as neurotechnology, sort of standing on the shoulders of giants is really important. You don't have to reinvent the wheel every time. It makes sense to build off stuff that's open source and that already really exists.
Yeah. Well, and we're just trying to make sure, because there's just a gap right now in the web where it's like, now we have the performance capabilities to do all this real-time processing, blah, blah, blah. Basically all the most convenient like networking, data layering stuff we could do, we could just do it in the web and then Node.js for your backend. And there's no complaints. It's just a lot of tools are going to, like, we have to redevelop a lot of stuff that's like very widely available, like in Python or in C or whatever.
Sure. Well, I think
just making sure that all is then usable. Sorry.
Yeah, definitely. I mean, the accessibility that this allows, that open source technology in general allows, is really important for helping people get into the field, because, before some of these consumer and open source like neurotech devices came around, then devices would cost tens of thousands of dollars and maybe need some sort of license to to operate. So it's really great to see that.
I mean, that's still the way it is, actually.
Well, it is. No, it is. But it's becoming with companies like OpenBCI and what you guys are doing, and even others, like we know GTech has an open source ish version of the Unicorn, and it's just. Well, yeah, I mean, it's good to see because it makes it more accessible.
We've had the opportunity to talk to a lot of these guys as well, and sort of hear where their thinking is at. And I mean, at least where we're at with web technologies, almost nobody, even maybe except web, like the general web devs themselves, don't really have a conception of this. There's still a big filter between like business incentives and trying to build your own sort of ecosystem that you have your products and your consumers in, right? Versus like, oh, let's actually build an infrastructure that we all benefit from and makes it actually accessible for everybody. Because ultimately we're fulfilling health needs for this stuff. Not, it's not just cool and cute, right? I don't know, I at least want to be a voice for that. I mean, I guess I'm a dirty socialist or something, but like really, like we need to come together on this stuff.
Yeah, definitely. Well, a lot of that's reflective in the way that you've developed out the platform. We were scrolling through it the other day and just looking at the devices that are supported. And, it was several pages of scrolling, which is really good to see and is not something you can say for most of the software that's out there. So yeah, what does your platform support, and like how interoperable are these different devices, like with different applications that you have?
Yeah, so I guess I could speak on that. It's worth mentioning that the app.brainsatplay.com, the Brains at Play platform that you engaged with, is a pre-alpha prototype that we probably haven't touched for a couple months. We ported it over from this sort of big monolithic repository. I think it was December, but we didn't change anything, and some things may be broken there. But at least in that instantiation, we support, Muse, OpenBCI, Free, G, HEG, anything we could get our hands on. We even have Neosensory, so that's a company founded by David Eagleman to do like haptics. And another thing that was interesting is we actually integrated with BCI 2000. So that's like one of the standard BCI software. But BCI 2000 is used by a bunch of research labs for intercortical devices to help people with ALS. And so they created a web extension, and we just integrated that. But so those are all interoperable. We just pipe the EEG data or FNIRS data into a standard data structure that's parsed, the same regardless of the device you have. It's all downstream. Right now, in terms of more recent developments, we've created a data streams API. So that's wrapping the Web Bluetooth, Web Serial, and WebSocket APIs in order to allow you to just get any time series data in a standard format that's similar to some of the other APIs on the web.
And we're coming up with, like I had this whole Atlas system that we built to mash all the data into one big object and then provide sorts and stuff. And so like I've broken all that out into libraries where I provide like standard like object formatting for whatever types of data can be coming in. And then like, gosh, we built our whole own like backend system that lets us even send that data and store it and update it, or like stream it in a very optimal way. So you can just like assign objects to some streaming thing and just have callbacks that run when things update. And just doing a lot of really just basic stuff like that so that we can make it much easier. Like our libraries for Brains at Play were not digestible because it's just us just going and building stuff. And then now we're really focused on like, okay, let's make this, if not, mimicking some other ready standard, then like making it super duper easy to use. So there's like very little learning curve, and it's not making you use much more than what you would already do in JavaScript anyway, like in terms of like the thinking patterns that you would use.
Laying this long-term groundwork for the future of the platform. When are you guys planning on releasing the platform? Do you guys have any ideas in that regard?
I think our development is no longer even
sort
really
of an ongoing
organized around
release
the platform thing. That's something that I would be quite comfortable scrapping up until we gain some partners. for instance, we worked with the BCI for Kids program at the University of Calgary. So they build brain-controlled games for kids with cerebral palsy. I was in contact with the developers of BCI 2000 Web, and they all are really interested in using the web as a distribution platform for applications for their users. And the platform is one of the best examples of how to do that in a practical way. We currently don't have like ongoing projects with these groups, but that's something that we would very likely spin up in the future. And that would sort of reinvigorate the idea of this platform. Other than that, it's largely around, again, all this API development. I would still consider most, if not all of those, to also be at the alpha, if not pre-alpha phase. And the way in which we actually push forward on that is getting partners and contributors to engage with it and tell us what they want and what they'd like to see out of it. Because otherwise, it's kind of hard to say, hey, we've solved all the problems without a lot of people trying it out. I would put the timeline on probably late this summer, mostly because we're starting to accumulate partners and I'm going to be graduating. So it'll be a little bit easier to just hunker down and do a lot of this documentation work.
No, definitely. And kind of in that vein too, I understand that you've both been working on a paper that goes into this stuff as well. The idea of having an open web and why that's important to put these tools up there. And so, yeah, if you could, I understand you're fairly close to publishing or to submitting. Could you tell us where you are with that and where people will be able to find it and what it's about?
For sure. Yeah. So the manuscript is due on April 30th. We're going to go through a couple more rounds of revision, largely around reframing all of the focus, more to be around some of the practical ways in which we've engaged people, both in the open source community and beyond. So, for instance, that whole Livewire event, the BCI for Kids program, all of those things. The core of the paper is really that brain-computer interfaces within a research context have never really been developed for use at home. There's been a recent push for user-centered design where you actually design with end users with the goal of actually getting it into their homes. I talked with the person who publishes this. Her name's Andrea Kubler. She's really great. She's a researcher up in Germany. And what she told me is that she hasn't gotten a lot of traction despite a lot of the publications that she's put out around this because of funding considerations. So there's just not a lot of support from either science funding, so the NSF in the United States, or sort of health funding, so the NIH here as well, because one considers it to be too health oriented. So the NSF goes, well, this is too human, right? This is oriented more towards like health outcomes. And then the NIH goes, well, this is just, it doesn't work very well. So we can't take this either. So a lot of the times these sorts of projects fall through the cracks, and adding the component of actually interfacing with users.
Okay, so how can people get directly involved with Brains at Play? Is there any way that people can contribute to the code base or maybe get involved in a organizational standpoint, anything like that?
So best way, if you really want to contribute to the code base, we're still getting like organized. Like, I mean, this is 6 months of getting organized. We're getting our libraries all sort of pieced together. We've got our map now set out, but we're still just trying to put everything back in place. And then from there, we're going to actually be doing all the documentation. And then from there, we'll be like, okay, here's what we're finally like offering. And then from there, it should be a lot easier for people to like actually navigate what we're doing and then find places to contribute. If right now you're like, hell yeah, this sounds like awesome. Well, you're going to have to get in touch and just like work with us a bit to find out where you can contribute if you want to do code. Otherwise, just sit tight and wait for our announcements.
And we'll have links to all that stuff in the description of the podcast episode.
You'll put your Discord link there, a link to the website, anything else, maybe the paper when it comes out. So yes, we will definitely be sure to cover all of that. And before we go, I know we've spoken a lot about the technology, but is there anything about Brains at Play that we didn't cover that you'd like to communicate to the viewers, where you think it can go, or other features that weren't mentioned?
Sure. I mean, what we're going to work on is making this like a multi-sensor, software library plus application base, and then it's meant to try to bring all this tech together, and then also be like proof of concept for like, oh yeah, we can scale the software like basically straight from a researcher's context right into homes once we can get a production model for that, and like really trying to bring people together around this idea that like we can sort of get away from the competitive scheme. I mean, there's billions of people that need health care. So like really trying to figure out how we can put this together in a responsible way as a community where we're leading the technologies, and also like, doing cool stuff, learning cool stuff in school. Ooh, brains, neuroscience, right? And sensors, and robots, I don't know, whatever. But also like, there's serious consequences to making this stuff really accessible and providing a lot of these tools that have a lot of sort of mysticism around them. I mean, like, okay, signal analysis by itself is like, I've found like 3 or 4 people that really understand it and know it's not voodoo. But then those are like $1 million algorithms that they're writing just because the products that are being propped up by these otherwise fairly basic things like technical problems, if you actually go and get educated in those strands, like these are like 101 things you're solving that are end up putting up all these really expensive products right now. A lot of that needs to go away. Like we need people to just contribute the stuff in an open context, and of course through a scalable infrastructure altogether. So we're hoping to sort of be at least one of the bases for that, and trying to convince some of these bigger companies to get on board. If not using our libraries as a base, then coming up with something that has the same spirit at least. And our job is just to try to make that like our stuff as good as possible, so we really make a strong case there.
Well, thank you both once again for coming on to the podcast. We appreciate the conversation, and I love the goal of what you guys are doing here. I mean, it really is very altruistic, and it's great to see somebody kind of pushing the field in a way that is very open and willing to collaborate.
Thank you, guys. It's fun.
Yeah, thanks for having us.